Ready to go live. Yeah,
Yeah,
starting. Okay.
yeah, Dr. Ram.
Yeah, very warm welcome to all of you for this special program organized by Vigyan Prasad in honor of Ramanujan on his 100th death year. 100 years ago, unfortunately, very young Ramanujan passed away. Yet his mathematics and his legacy are still living and providing inspiration to one and all. As a part of celebrating Ramanujan's memory and also popularizing mathematics and addressing math phobia, Vigyan Prasad is organizing number of programs called Ramanujan Yatra, in which we are organizing programs in various Indian languages and are also inviting special guests from international maths community to talk about Ramanujan. This is one such event as part of this Ramanujan Yatra, and I welcome on behalf of Vigyan Prasad and also the Ramanujan Yatra committee, all people who have joined us through various social media for the program, and also various experts who are there in our studio for conducting this program. Initially, I would request our director of Vigyan Prasad, Dr. Nakul Parasar, to explain the background of this Ramanujan Yatra and take forward this program. After this introduction of this Yatra, we will have Dr. Ramanujan introducing our speaker, and then the speaker will provide his lecture. And people who have joined us through the social media, you can leave your comments even in between the talk in the chat box. We will be able to look up your comments, and we'll be able to pass on to the speaker for a very interactive session. So we would urge and invite all people to leave your comments in the comment chat box. So may I request our director, Dr. Nakul Parasar, to introduce Ramanujan Yatra and also begin today's program. Thank you.
Very warm good evening to everyone. It's indeed a pleasure for entire Vigyan Prasad to have been privileged by the acceptance of our request to address today's lecture. Professor Don Zagier of the Max Planck Institute of Mathematics in Bonn, Germany. Sir, on behalf of the entire organization and my team that has been relentlessly working hard for all these months ever since we started the Ramanujan Yatra, we welcome you wholeheartedly and thank you for accepting our invitation. As Dr. Ramanujan rightly said, the mathematician, the legend, Ramanujan, passed away at a very young age on April 26, 1920. This year, we had planned to organize a big program in Kumbakonam, the birthplace of the legend. However, due to lockdown and COVID, we couldn't do it. But ever since we've been organizing subject matter expert lectures from all over the world, and in this process, this month's lecture, we are honored to have you with us. We welcome you once again. As Dr. Ram Venkateshwar rightly said, we've planned a series of lectures in Indian languages, and I'm glad to share with you that most of the Indian languages have been covered so far. Entire South Indian languages have been covered, and we have been moving up from south to north, and we have covered Tamil, Telugu, Kannada, Malayalam, Marathi, Gujarati, and also Assamia, Bengali, and recently we've completed Hindi and Punjabi as well. All the length and the breadth of the country, the languages that we mostly have are getting covered as quickly as possible because we are approaching December 22nd, which is the birth date of the legend. The time 26th April till December 22nd is when we thought we'll have this marathon journey of our lectures, and that's where we are. In this whole journey, I really would want to, thank and appreciate the efforts of Dr. Ramanujan from the Indian Institute of Mathematical Sciences, from the Institute of Mathematical Sciences for having supported us in this program wholeheartedly. Sir, we remain indebted to you for your support, your encouragement and patronage, and also to the entire team of Arivel Balage, Shri Shivakumar and Bhaskar ji, for having supported and gotten to this level. So without coming in between the lecture that we are all waiting for, particularly from Professor Zagier, I will now end my welcome address here and would request Professor Ramanujan to invite and introduce our today's speaker. Over to Dr. Ramanujan with a lot of thanks for all your support so far. And we look forward to your patronage for the many more programs that you intend to plan hereafter. Thank you so much. Thank you, Professor John Zagier. Thank you, Dr. Venkateshwaran and Dr. Sri Kumarji as well. Over to you, Professor Ramanujan. You mute, sir. Professor Ramanujan, you got to unmute your mic.
Oh, sorry. Yeah. Thank you very much. It's my pleasure to welcome the speaker of the day, Professor Don Zagier. I must mention that the title of the talk is The Most Beautiful Formulas in Mathematics, as you can see in the trailer that's coming along with the screen here. There is a mistake in the title as it was announced earlier. Please make sure that you understand. It's a quotation, and you can't have someone better than Don Bernard Zagier to talk about these most beautiful formulas of mathematics. Professor Zagier is one of the great mathematics teachers alive that we know of, and I would call him a teacher's teacher. He has taught a whole generation of people on how to communicate mathematics as well, apart from talking he's done some deep work in mathematics. He's an American-German mathematician whose main area of work is number theory. He's one of the directors of the Max Planck Institute for Mathematics in Bonn in Germany, and he was earlier in Collège de France. He's a distinguished staff associate at ICTP. He has worked on modular surfaces. There is the Gauss-Zagier formula, which is very famous. His contributions in mathematics are very deep. He won the Cole Prize in number theory. He won the von Staudt Prize. He got the Gauss Lectureship of the German Mathematical Society. And he's a member of the National Academy of Sciences, the Royal Netherlands Academy of Arts and Sciences. And one of his most beautiful things that I know of is a very short and beautiful proof of Fermat's theorems and sums of two squares. And so there is a lot about Professor Zagier that I should mention. But what we have here is Professor Zagier to tell us about the Rajas-Ramanujan identities, the most beautiful formulas in mathematics. It's great to have you here, Don. Over to you. We all look forward to listening to you.
So thank you very much, Ram, for these kind words, partially rather undeserved. When I first heard about this lecture and was invited to give one of the Ramanujan Yatra lectures, I was very excited and flattered because, of course, Ramanujan has been one of my heroes, or my main hero in mathematics, since I was maybe 17. And I think that's the case of half the mathematicians, at least number theorists in the world. He's every mathematician's favorite mathematician. So I'm very happy to be part of today's celebration. So I will start. I add this word, as well as being his name, was to test the size of the writing. I can now add the rest of the words. So the two most beautiful formulas of mathematics of my title, this is a quote, not a quote from any particular person, as far as I know. it's folklore. One hears very often that when mathematicians are asked to name what they think is the most beautiful formula in all of mathematics, the most elegant, then very often they have not one formula, but a pair. These are the Ramanujan identities. I should, however, be honest and say that there's a rival. There's a single formula, which is maybe even more beautiful, but I will talk about it later. I think you'll forgive me. This formula is also due to Ramanujan and is directly related to the pair of Ramanujan identities. So that's going to be my topic, and as you'll see, I hope it branches out in many ways. I could talk about it for many days, but luckily I will only talk for 1 hour. So these identities are formulas, and every formula in mathematics has the form that the left-hand side is the right-hand side. And so what will occur on the left-hand side will be two functions, g of q and h of q, of a special form discovered by actually both Robs and Ramanujan. And these are called Q hypergeometric series. So before writing what they are, maybe I should say one word. This lecture is, of course, meant to be as broadly understandable as possible, so I will try to explain the meanings of words that may not be familiar to everybody, but Q hypergeometric series is not familiar even to many mathematicians. It's a somewhat special notion, but very beautiful, and was at the center of Ramanujan's scientific work in many, many of his things. So in 2 words, a classical hypergeometric series, these were invented by Euler and studied later by Gauss and by many famous mathematicians, Kummer, many others. This is a sum of a very special form. It's a power series. So sum an x to the n. And what makes it a hypergeometric series is that each coefficient, an, is the product of the previous coefficient, an minus 1, times a rational function of n. A rational function means the quotient of 2 polynomials. I won't give an example because I won't talk about them, but a Q hypergeometric function is the analog of that and has become very important in the 20th century also because of many connections to physics. This Q you can think of as the Q of quantum theory, although the letter Q has been used long before quantum theory existed. So these are series. The variable is now called Q rather than X traditionally. But now we have a sum of the form sum an of Q. And the difference to the classical hypergeometric function is that each an of Q is the previous an minus 1 of Q multiplied by a rational function, but not of n, but of both Q and Q to the n. But a fixed rational function independent of X. So this is a rational function, let's say R of Q and Z, is again a rational function, a quotient of polynomials. So those are the words, and now to make it clear what this is, I give you the first of the 2 Ramanujan functions. So this function is, of course, Q hypergeometric, as I told you, and it's the sum of a fraction. The numerator of the fraction is a power of Q, but it's not Q to the nth, it's Q to the power n squared. And the denominator of the fraction is 1 minus Q times 1 minus Q squared up to 1 minus Q to the n. So indeed, you see that if I call this thing an of Q, then indeed you see that an of Q you get from the previous one. The previous one was 1 minus Q up to 1 minus Q to the n minus 1. So there's an extra 1 minus Q to the n at the denominator. And the numerator, q to the n squared, is q to the n minus 1 squared times q to the 2n minus 1. And so this one would be the function r of q, q to the n. It's a polynomial. If you want, I can write out r of qz in this case would be z squared over q times 1 minus z. So a quotient of polynomials. So this is indeed an example of this wonderful class of Q hypergeometric series on which Ramanujan made so many contributions. So there are many, many, many books. It's a big field. So let's look explicitly what this says. The point is that any Q hypergeometric series is also a power series. We can expand it as a power series. So let me show you how that works. In this case of the Rhodes-Ramanujan formula, the first one, the first term A0 is just an empty product, so that's 1. A1 of q, so maybe I should have written this out. This is 1 plus q over 1 minus q over 1 minus q plus q to the 4th over 1 minus q squared, 1 minus q times 1 minus q squared, plus q to the 9th over the triple product, etc. So if I write out the first few terms, then if I expand this as a power series, well, 1 is rather easy. It's 1 plus 0q plus 0q squared, plus maybe I don't have to write all infinitely many zeros. Then if I take q over 1 minus q, it starts with q, but this is the geometric series that we learn in high school. 1 over 1 minus q is 1 plus q squared plus q cubed. So this is the geometric series. And the next term, a2 of q, starts with q to the 4th. So it starts out here. And then you divide by 1 minus q again, so that would be 1 minus q to the 5th. And if I only divided by 1 minus q, I'd have q to the 4th plus q to the 5th plus q to the 6th. But I have a second term, q squared, so the next term is 2q to the 6th, and so on. Of course, I could compute any number of terms. And similarly, a3, but a3 would start with q to the 9th. So we don't see it. So when I add this all up, if I just add, this line is meant to be the summation sign, then you see g of q is 1 plus q squared plus q cubed, but then it becomes 2q to the 4th plus 2q to the 5th plus 3q to the 6th. And of course, this series goes on, and so I didn't remember the number. On my computer this morning, I checked that, for instance, the power of q to the 100th is 74,040. So this series goes on, and these numbers are quite mysterious. And the question is not what these numbers are, but what are the properties of this whole object. So now comes the wonderful discovery. If I look at g of q, and if I look at the expansion that you see here, 1q, q squared, q cubed, then up to q to the 4th, it looks just like the geometric series that we already saw, 1 over 1 minus q. So it looks like it starts 1 over 1 minus q. But if I just wrote 1 over 1 minus q, that would give me 1q, q squared, q to the 4th. But there's an extra q to the 4th here. It's not 1, it's 2. And so I should multiply by another term, 1 minus q to the 4th. Now that would give me the q to the 4th, the extra one, and a q to the 5th, because q to the 4th times q to the 1. But now we see we only have 2 times q to the 6th, but we have 3. So if I continue this process, you can do this with any power series at all, starting with 1, you can uniquely write as 1 minus q to some power times 1 minus q squared to some power 1 minus q cubed. But in general, these powers will be random numbers. But here, that's the whole point, they're not random at all. When you do this a long way, by hand, as of course Ramanujan did, you find that the powers you get are always in the denominator, nothing in the numerator. They're always to the first power, no 1 minus q to the 4th squared, let's say. But you only get certain numbers. And this is the first Ramanujan identity. And here the discovery is that you get only terms 1 minus q to the m, where m is congruent, well, number theorists would write congruent to plus or minus 1 mod 5, which means m is either 5n plus 1 or it's 5n plus 4. So you see the exponents are 1, 4, then 5 plus 1, 5 plus 4, 10 plus 1, 10 plus 4, etc. So this is one of these amazing identities. And of course, the big surprise, you start with something a little complicated, but there are no 5s. It's just q to the n squared over this product. And suddenly the answer has this strange periodicity of period 5. Now, it's a pair of formulas, as my title says. The other one I can give much more briefly because it's exactly similar. The denominator is exactly the same. The numerator is q to the n squared plus n instead of just q to the n squared. And so this one now starts with 1 plus q squared over 1 minus q plus q to the 6th over 1 minus q times 1 minus q squared, etc. And so if you multiply this out, well, I don't remember these numbers. When I was young, I was known for being able to give lectures where I remembered all the numbers in my head. And people would bet how long I would talk before writing a big number on the board by heart. But now I can't do it anymore, so this one starts, well, it doesn't really matter. And again, just for fun, I computed the 100th coefficient. It's 46,477. So these numbers grow, they're positive. And now when you do the same thing as here, and multiply it out, you find that this time we have 1 minus q squared, 1 minus q cubed, 1 minus q to the 7th, 1 minus q to the 8th, and so on. And here the exponents 1 minus q to the m, where m is congruent to plus or minus 2 mod 5. So it's either 5n plus 2 or 5n plus 3. As you see, 2, 3, 7, 8, 12, 13, etc. So these are these rather amazing formulas. So as their name says, they were discovered by both Rogers and Ramanujan. Leonard Rogers, a British mathematician, was in fact 20 years earlier. So Rogers discovered them in 1894 in a paper that was not widely known. Certainly Ramanujan didn't know it. R rediscovered them sometime, we don't know exactly, before 1913. But then he discovered the paper. He was informed, or he found the paper by Rogers 2 years later, and then they wrote a joint paper. I find that very nice, in 1917, I believe, or 16, it doesn't really matter. I have it written down, 1919, in fact. So the proof that was 1 year before he died. As we know, they found a new proof and published them together and published as a joint paper. And also the famous German mathematician Schur independently found it in 1917. And since then, there are many, many, many proofs using ideas from many parts of mathematics and also of physics, for instance, vertex operator algebras. So that's that story. But I promised you I would give you another identity, which is maybe even more beautiful and which is related to these. So I want to do that now. So my next identity, my next formula, involves what are called continued fractions. So these are certainly more familiar to mathematicians than Q-hypergeometric series, but still, since I want to exclude as few people as possible, and it's not that well known, I will say very briefly. So an ordinary fraction, I think everybody knows, is an expression of the form a divided by b, where a and b are numbers. Or sometimes they're more complicated things like polynomials, but let's say numbers. But a continued fraction, well, it's exactly as the number says. You start with a fraction, so it's a numerator divided by a denominator, but the denominator is itself a fraction. And a fraction has well, you could think of it as the integral part and the fractional part. It doesn't have to be, but I split it into two parts, the original denominator, and now a new fraction. So let's call it A1 over B1, A2 over B2, A3 over B3, etc. So such an expression, an infinite expression, is called a continued fraction. So the most famous example and the simplest example is the number phi, which is 1 plus the square root of 5 over 2. So that's about 1.61833. This is the so-called golden ratio. I think everybody has heard of it. It's together with pi, perhaps the most famous number in all of mathematics. It's supposed to be the most harmonious proportion between two things. So if two things are in the ratio, in the golden ratio of 1.618, they're in the ideal relationship to each other. It occurs that's true for both the works of man. So many classical buildings, I think even Egyptian, certainly Greek, where the ratio of the side to the width was the golden ratio, but also in many places in nature, in the distribution of seeds of a sunflower or something. So this beautiful ratio occurs in many places. And what makes it beautiful is the following fact. So if I take the so-called golden rectangle, which means a rectangle which is in the ratio of 1 to this phi, and if I take unfortunately I can't draw very well, so it should be, I think that's more accurate. That's 1.618033. So if you take the golden rectangle and you remove from it a square, then what's left over is again a golden rectangle. And that uniquely determines what this most harmonious ratio is. So what does that mean? Well, this distance is 1 because I subtracted a square, so this is phi minus 1, and this is 1, so phi minus 1 is 1 over phi. So what you see is that picture tells you that the golden ratio, of course you can do this just by solving the quadratic equation as we learn in school, the golden ratio satisfies that phi is equal to 1 plus 1 over phi. So 1 over phi is 0.61803. But now I can iterate this. So I've expressed phi in terms of itself, but now the new phi I can write again in terms of the old phi. And now I can put this again. And so if I keep going, I find that this is exactly the simplest possible continued fraction where every ai and every bi is equal to 1. So this is the simplest example of a continued fraction where all the a's and all the b's are equal to 1. So is this still visible? Okay, so of course Ramanujan knew this very well. This is child's play, even for us, and certainly for him. This is too low, it casts a shadow. So he asked the question, so I'll call this function R for ratio, but also for Ramanujan. We take, instead of the one I just wrote, 1 plus 1, I'm going to put my variable q. Now, if I just put q every time, I'm not going to do that, so I'm going to change this in a second. Then this would say R is 1 plus Q over R. That's again a quadratic equation. You can solve it immediately. It's not interesting. But what Ramanujan did is look at the series where the denominators, the BI, are always 1, as before, but the numerators, the AI, are powers of Q. Q squared, Q cubed, Q to the 4th, and so on. So that's the Ramanujan continued fraction. And just like the G and the Q, you can expand this out. So it's not very interesting in the sense you get some numbers, but you have no idea what they mean. They're smaller than before, and they're positive and negative. So for instance, now the 100th coefficient is only 855. Before it was 74,040 and 47,996, I think. So now, the first connection, but this is not yet the most beautiful formula in mathematics, but this is the connection to the Ramanujan formula. This series is the quotient of the two that I had before. Ramanujan discovered that and presumably had a proof, although he wasn't a big one for giving proofs. So if you now add if we add the Ramanujan formulas, so this G and H are defined by those sums that I started with. This was G and H is now covered up. But if I now write out that sum, then I hope it's correct. Then remember G was 1 over 1 minus q, 1 minus q to the 4th, 1 minus q to the 6th, etc. And in the numerator, we have 1 minus q squared, 1 minus q cubed, 1 minus q to the 7th. So now everything has been put together into a single formula. And so the power of each 1 minus qm in this formula, the question mark is 1 if m is 5n plus 2 or 5n plus 3. It's minus 1 if m is 5n plus 1 or 5n plus 4. And it's 0 if m is 5n. And in other words, it's a product, 1 minus q to the m to some power, and those powers are periodic with period 5. And again, the really amazing thing here is the appearance of this number 5, which actually in my entire story, there are 5s everywhere, and every 5 you see is connected to every other 5, except maybe for these two. So they're all connected. It's about 5, and you see that even in the special case, if you take q equals 1 here, of course here you can't, every term is 0. This form is only true if q is between 1 and minus 1. But here I could take q equals 1, I get the golden ratio, and that also has the 5 in it, 1 plus square root of 5 over 2. So that is, as I said, the formula that many people call the most beautiful in all of mathematics, and it's actually fairly hard to disagree with that. So now I want to go a little further. The next story I tell, I was actually personally involved, so it's a nice place to tell it. It's a story I think I haven't told before. So this story has to do with the so-called lost notebooks of Ramanujan. So I don't know if you can see this, but here are the lost notebooks of Ramanujan in a beautiful edition that was produced in India and given to me as a present when I visited in 1987 for the centenary of his birth, so 33 years ago. And this lost notebook, which it actually wasn't all that lost. It was somehow mislaid, perhaps conveniently mislaid by a mathematician whose name is, of course, known, and it wasn't found for many years. So it was a mislaid notebook, which was eventually found in 1976. So the lost notebooks were rediscovered in 1976 by George Andrews. And then he and Bruce Bernd is a person that maybe many of you know because he's very famous for his work on Ramanujan, but he gave one of the earlier Yatra lectures this year. The two of them decided, they had the plan, so Andrews found it, they made the plan to publish all of the notebooks. But not in the form I showed you, which is a facsimile. This big book is just a facsimile of the handwriting. It's very interesting, but there are, of course, no proofs, no indications. It's very legible, but one has no idea why any formula is true. And they decided that since these formulas are so important, that they should be published with complete proofs. This took many years. It finally came out in 5 volumes. One of them I've here. It's one of my favorite books. My wife gave it to me as a birthday present already many years ago. That was volume 1. And volume 5, which I believe will be the last one, only came out 2 years ago. So this was a Herculean project, a mammoth project, successful and very, very, something the community is certainly very grateful for. And the idea, as I said, was to give proofs for every claim. Ramanujan himself essentially never gave proofs for anything. Sometimes he certainly had proofs that we would consider rigorous. Often he had an argument that we wouldn't consider rigorous, but that any competent mathematician could take and think about and say, of course, that indeed he found the reason. In some cases, it was maybe just intuition, or he had some knowledge we don't know. In some cases, of course, he was simply wrong. And in a few cases, it was impossible to decide whether he was right or wrong. A few cases remained open. And these editors didn't like that. They wanted to resolve every mystery. So to give either proofs or disproofs if it turned out to be an incorrect or statement needing some correction. So one of these formulas, in particular, I have written down the name because I wouldn't remember. It's in the second notebook. Page 289, formula 4. It was a very strange formula. And Bruce Berndt wrote to Henri Cohen, who's a friend of mine, asking if he could not even prove it, but understand what it meant. And Henri Cohen did understand something, but I couldn't prove it, so he asked me, and I did finally prove it. So what the formula said, I'm copying now from the notebook, it's a continued fraction, very like the one we saw, except here there's a minus sign, and here there's an extra x. Here there's a plus sign again, and no extra x. Here there's a minus sign again, and the x. So every other term is plus and just q to the n, if n is odd, and the other terms are minus and with an x if n is, if n is even, it's 1 plus q to the n. If n is odd, it's 1 minus q to the n times x. And what Ramanujan wrote is a formula. So as I said at the beginning of my lecture, every identity in mathematics has the form left-hand side equals right-hand side. But this is an exception. So the formula that Ramanujan wrote, this time the a's are always the same, they're x. The q's are, well, the first is q to the 1, but otherwise they're q to the 4n. So q to the 8th, then q to the 12th, etc. Well, this would be fine if it were a formula like every other formula in mathematics. There's a left-hand side and a right-hand side, and they're equal. So what's not to like? What's not to like is that they're certainly not equal. Any mathematician looks at this and says, as a power series, this starts 1 minus qx. That starts q over x. I mean, they aren't even at all equal. I mean, there's nothing equal about them. Nor did Ramanujan, of course, say that they were equal. What he wrote in his notebook, but as usual, he didn't explain. Of course, he was writing for himself. It was a private notebook. He didn't have to explain. He wrote that these are nearly equal. And so the question that Bruce Berndt asked to put this in the edited works with the proof, first, what does it mean? What is the statement? Well, that part, now I think I slowly have to start erasing something. Where's the, here. So this is the German system which gets the board very clean and the speaker very dirty. Unless he's extremely careful. So where was I? I'm losing the thread. Here we had this nearly equal. So Henri Cohen said, well, maybe he simply meant numerically equal. And indeed, he did many computations. That turned out to be right. So an example, if I take x equals a half, and q, so Ramanujan wrote that for q between 0 and 1, and x also between 0 and 1, but x actually can be more or less anything. So let's say, as an example, I take q to be 0.9, so fairly close to 1, but not very close, 0.9. That's a 9, that's a q. And x is a half. Then if you take this expression and you compute it on your computer, it's of course very easy. The left-hand side is 0.776734018 ... But the right-hand side, it's not the same. As I said, the two sides are definitely not equal, but it's 776734018. So the first digit that changed is way out there. And if I take, as an example again, x equals a half, but q is 0.99, I won't write out the numbers, but they agree to 96 digits. So indeed, he had discovered something very beautiful, and it was exactly, as he said, he couldn't have been more honest. These two numbers make sense, they're numbers, and they're equal very nearly. But then you have to understand why and prove it. I did, in fact, I wrote a small paper, whatever year it was. It was actually quite a lot of work. And when one graphed this function as a function of x for a given q, if q is near to 1, then if you took f minus g, it tended very, very quickly to, well, here this was f over g. It oscillated. So there was an oscillatory behavior, but it became extremely fast, as you see in this, extremely small, as you see in these examples, as, well, that you don't see it in this example. It becomes small and fast. So let me give an example. If q is e to the minus epsilon, so epsilon is small, then the left-hand side minus the right-hand side. Oh, sorry, I didn't give the end of what I did in the original case. I left out one nice formula. Sorry. So let me do first. If x is 1, which is the simplest case, I didn't say, but maybe I should have said, if you look at this formula, I said it reminds one of the Rodda's continued fraction, but you even see that if x is minus 1, then the left-hand side, now the x's don't matter, and all the signs become plus. It's exactly the Rodda's Ramanujan function, or the original continued fraction. And if x is plus 1, but that's a different value, then the right-hand side is exactly q divided by r of q to the 4th. So, but that doesn't tell you why they're related, because it's different values of x and the right-hand sides are different. But at least you see it's connected to our continued fraction. And so what I showed in the case when x is 1 first, then you can see it very nicely, is, so I'll actually write the complete formula. I should have written it first, but I forgot, so I'll write a little smaller. If x is 1, the left-hand side is a constant. Well, it's not quite a constant. It's e to the minus epsilon over 5, so that's very near to 1, divided by the same golden ratio we had before, 1 plus the square root of 5 over 2. That's the leading term, but then there's a correction term, which is much smaller. And the correction term is the square root of 5 times e to the minus pi squared divided by 5 epsilon. And there are more terms, which I won't write. So if epsilon is very small, then 1 over epsilon is very big. And pi squared over 5 times epsilon is even bigger. And so minus it is a very negative number. E to a very negative number is extremely small. And so this is virtually equal to 1. And so the left-hand side is almost exactly q to the 1/5 in this case over the golden ratio. But the right-hand side is exactly the same pre-number, e to the minus epsilon over 5 divided by the golden ratio. But now the correction factor is exactly the same. Well, the first term, there are further terms which are, each one has its own expansion, but now this is a minus sign. So you see now exactly what Ramanujan meant, that they're very nearly equal. These terms are exactly the same, and this is much, much, much smaller. If epsilon is 1/100th, as in my second example, then this difference will be 10 to the minus 96, and that explains, once you've proved it, it explains this very, very high agreement. So more generally, I'll just write it briefly because it's kind of fun that there's an oscillatory term that you wouldn't expect. If you take a general x, then we define an angle by taking the logarithm of x and dividing by epsilon. So as x goes to 0, this will change, this angle will change, go around the clock many, many times. And so you get highly oscillatory behavior. And the left-hand side turns out to be a certain constant depending on x divided by epsilon times the cosine of this angle. That was the final result. So it's both oscillatory and extremely small, sorry, minus. And c of x is just a function. It's given in terms of the dilogarithm, which is a wonderful function I've often lectured on. It was one of Ramanujan's famous favorites, but I won't talk about it. I'll just give two of the values. Pi squared over 4 and pi squared over 5. So the pi squared over 5 is the one you see here. But for every x, there's a similar exponential behavior. So now, the time is advancing quickly, but that's good because that's what time is supposed to do. This discovery, which I'm sure Ramanujan knew this. He certainly knew, maybe not the complete expansion, but he certainly had part of this. The amazing thing here, or not the amazing thing, but the important thing here, is that we've gone from one number q, which is e to the minus epsilon, to another number, let's call it q tilde, or capital Q, which is e to the minus, not epsilon, but a constant over epsilon. And the constant is actually pi squared over 5 in this case. But as I said, in other cases, it might be something else. So this is a strange behavior where you have an exponential and you have another exponential, but the two exponents are essentially inverse to each other. And this is the phenomenon of modularity. So that will be my next, in some sense, final theme for the rest of the talk. I'll give several examples. So this phenomenon of modularity, the full formal name is the theory of modular forms, which is many of the early discoveries were actually made by Ramanujan, but in a sense, unwittingly. He never saw the theory as a theory, but it's become an extremely important branch of number theory. It's my specialty. I love them. So modular forms, and in the form that Ramanujan found modularity, he typically had a Q and a Q tilde, let's call it. And he wrote the exponents as maybe, well, e to the minus alpha and minus beta. And typically he said, if alpha beta is pi squared, so this was a typical entry in the notebook, then something happens. So he looked at functions which involved a Q, like these Q series we've been seeing, but where there was some relation with Q and Q tilde when the product of the exponents was, for instance, pi squared. And this is exactly what's now called modularity. So, as I said, he didn't really understood, certainly in Madras, when he worked alone, he found many of these formulas. I'll give one or two examples in a moment, but did not see the modular transformation as a transformation law. I'm looking for one nice formula I wanted to give, but I've lost it in my notes. It'll come in a second. It's maybe a little later. He found the formal transformations, but he didn't realize that it was important to actually change variables and think of alpha and beta as the correct variables. So he found many beautiful formulas. When he went to England, Hardy, of course, did know what modular forms were and explained it to him. And in their famous work on partitions that I was going to talk about, but we'll have to stop, the partition functions come from a Q series, hypergeometry series, which is modular, so that played a big role. But I don't think Ramanujan himself ever really internalized it. He never became an expert in the theory, but he knew, of course, what to do at the level of the Q series very well. So as I said, the idea is roughly, you have an f of Q, and then you have f of, so it's a Q series, as we had before, maybe Q hypergeometric. And the idea is that f of Q is related in some way to f of Q tilde. Sometimes this is a different f, but in the simplest case, the same f. And it may not always be alpha beta is pi squared. Actually, in the simplest cases, it'll actually be 4 pi squared. So I'll put that already, because those are the cases we'll have. So as I said, what people realized, actually they had realized before him, this was in the second half of the 19th century, that the theory of modular forms in its earliest form was developed. The first examples were due to Gauss, even earlier. What they realized is that if you have such a function, you should make a change of variables. So instead of writing Q is just a number, but maybe it's a complex number of absolute value less than 1, then Z is also a complex number, but it has the property that its imaginary part is strictly positive. So what that means, if I draw the complex plane here, 0, then Z is above the real axis, and Q is in the unit disk. And so you go from z to q by sending q equals e to the 2 pi I z. And of course, by Euler's formula, famous formula that e to the 2 pi I is 1, you can also change z to z plus 1 or z minus 1. And so when you have such an expansion, or if you have such a function, f of q, but you think that it's a function, I'll use a small letter, the corresponding function of z. If you think of it as a function of z, it automatically is periodic. F of z is equal to f of z plus 1 all by itself. You don't have to do anything. Conversely, if you have a nice function and f of z is f of z plus 1, you can write it as a function capital F of q, which is e to the 2 pi I z. But now the modularity property says that f of z and f of not 1 over z, because that would be in the lower half plane, that should be in the upper half plane, so minus 1 over z, are related. That is exactly what modularity means. That's the definition, essentially. I'm simplifying a little. So in the simplest case, and this is the only case I'll have today, they relate in the following way: they're equal up to a power of z. So k is some number, might be a half, it might be 7. It's called the weight. So that's the formal definition of modular forms. And I'll say briefly, because it's terribly important, but I won't need it for this talk, since f was already invariant under z goes to z plus 1, and it's also invariant up to a simple factor under minus 1 over z, those two very special transformations are special cases of what's called the modular group, which is z goes to any fractional linear transformation, a quotient of two linear expressions where a and b and c and d are all integers. And you need that the determinant ab minus bc is 1. If this is not familiar, just ignore it. But not only are these two special transformations special cases, so here a, b, c, d is 1, 1, 0, 1, here it's 0, minus 1, 1, 0, but in fact it can be shown quite easily that all such transformations are composed of these. And so if you have just these two transformations I said, then you automatically get a much more general transformation. And this is the beginning of what's now called the theory of automorphic forms. It's a huge field of mathematics, and these functions come in every part of mathematics and physics. So I'll just say that, but I won't really use that. But the thing to remember is that we have Q series where the values at Q and Q tilde are related if the product of the logs of Q and Q tilde is some constant. So that's what modularity is from a modern point of view. As I said, it wasn't Ramanujan's point of view, but that didn't stop him from finding some of the most extraordinary formulas associated with this field, sometimes with proofs, sometimes without, and essentially never stating the proof, even if he probably had one. So I don't want to forget formulas, so I should look at my notes again. So we have many such things. Let me give one example of a really beautiful formula he has. So these modular forms and modular functions occur, modular forms is what I'm talking about. They occur in many, many places in Ramanujan's work, but secretly. So since my theme is the Ramanujan formulas, let me take the original pair of functions, g of q and h of q. I won't rewrite the definition, you all saw it. But now I want to change them to a function of z, and as I said, I'm going to use small letters for the function of z, except it turns out that to make it behave well, you have to shift by the exponents by q to the minus of 60 and q to the 11 over 60. If you don't do that, it doesn't work. So now these two things are modular functions. They have the same expansion that I wrote before, shifted by 1/60th or 11/60th in the exponent. But now what happens is that these functions also have a transformation equation that's completely hidden. If you just look at the expansion, all you can see is what happens when z goes to z plus 1. You cannot see what happens when z goes to minus 1 over z. But in fact, something does happen. This is the hidden symmetry that is the essence of modularity. I'll take out the formula so I get the coefficients wrong. If you make these, it's not equal. I told you if it were a modular function, this would be simply g of z, but it's in fact a linear combination. It's 2 over the square root of 5 times the sine of 2 pi fifths times g of z plus sine of pi over 5 h of z. And the other form is exactly similar. It's 2 over the square root of 5 times sine of pi over 5, this time g of z, and now the minus sign, sine of 2 pi over 5. And the exact constants don't matter. But this is the basic reason, this is the reason, it's the only reason that the Ramanujan identities have a possibility of existing. Such beautiful identities somehow always occur when you have modular forms, because this huge symmetry forces many identities. And so to a mathematician who's used to modular forms, it's not a surprise that, so let me just write, G and H are modular forms. Here of weight 0, actually, because there's no power z to the something, z to the something. So this is an example, and therefore the R is also, which was the quotient, remember, and is an example of Ramanujan's genius. In his famous letter that he wrote in January 1913 to Hardy, after having unfortunately written to several other English mathematicians who threw his letters away, but Hardy took it very seriously, as we all know, and in that letter he gave 100 incredible formulas. Some Hardy could prove, most of them he couldn't, and some he had never seen anything like it. And one of them was exactly, remember, R was this famous continued fraction. So in his letter, with no explanation at all, of course, Ramanujan gives a closed formula, and it's an absolutely remarkable formula, so I want to write it down, but I have to get the numbers right, and now my notes are getting out of order. Here it is. It turns out it's slightly better, that's R, if I multiply by e to the pi over 5, the formula as he put it in his letter, then you get an algebraic number, and it's actually an extremely simple number. It's the golden ratio plus the square root of 2 plus the golden ratio. So an absolutely amazing formula. You take this infinite continued fraction with e to the minus 2 pi, e to the minus 4 pi, e to the minus 6 pi, multiply the whole thing by e to the pi over 5, and what you get is an algebraic number expressed in terms of the golden ratio. So this was one of the pearls in the letter, and this was one of the ones Hardy had no idea how to prove, although there were actually mathematicians in Europe earlier who would have known theoretically how to prove such things using modular forms. So as I said, they somehow played a role in the background of many of what he did, much of what he did. I still seem to have a little time, so maybe I was thinking I would have to skip some things, but I'll try to tell at least sketchily the main things I still wanted to tell you, show you. So let me give you a couple of examples of modular forms that were familiar to Ramanujan, and one of them he made an incredible discovery, which I'll show you. So here are examples of this. It's still written there, f of minus z. So let me give you 3 examples, all of which were known to him, and he proved beautiful identities that I won't give. One is called E4 today. I'll just put E4, E4 of Z or E4 of Q, whichever you prefer. So this is called the Eisenstein Series. It was discovered in the 19th century by Eisenstein, rediscovered by Ramanujan. And I can write it as a Q series most simply. It looks very artificial, but believe me, it's the right object. You take n cubed times q to the n over 1 minus q to the n. And you sum that up, and then you multiply by 240 and add 1. So this is a Q series, and what's interesting about it is exactly that it is a modular form. In other words, if I see this as a function not of Q but of Z, then E4 of minus 1 over Z is Z to the weight times f of Z, and the weight here is 4. which is the 4 that you see in the exponent. And similarly, E6, which will have weight 6, will start 1 minus 504q. It's exactly the same. The 240 becomes minus 504, and the n cubed becomes n to the 5th. And this is a modular form of weight 6. So that's, both of those are not trivial statements to prove that that remember means that if you change z to minus 1 over z, you have this strange relation. Then there's a much more beautiful one, which is called delta. This is often now called the Ramanujan function, and it's given by an infinite product. So I've used the product notation, but I mean, if I write it out, it's exactly like the products we saw in the two Rob's Ramanujan formulas, except that there the exponents were different, but they had period 5, and here the exponents are all 24, so period 1 if you want. So this is an even simpler expansion with 24. And then one amazing thing, I told you that because modular forms have this infinite symmetry, there are many, many identities which are then very, very easy to prove. And in this case, the famous identity, which of course Ramanujan knew very well, is this one. So if you take E4 as weight 4, so its cube has weight 12, E6 is weight 6, so its square has weight 12, the difference is weight 12, delta has weight 12, and you show, if you know the beginning of the theory of modular forms, that there are only 2 linearly independent forms of weight 12, and so these 3 forms must satisfy relation, and just by looking at 1 or 2 coefficients, you find this. So this identity, which is quite deep, you can prove in 2 lines if you know the definition of a modular form. Ramanujan didn't really know that definition, but of course could prove it anyway. So this was familiar. So this was not the exciting thing he discovered, although he did know that. But Ramanujan, I already gave you other examples. He was certainly not afraid to calculate, and obviously to calculate by hand. Nobody had computers. He didn't even have a whole lot of paper available. So he computed this. Now, this is from memory, and I hope I get it right, because I didn't actually check the numbers, but my memory of the first coefficients, it's the next one that I'm never sure of, 4470, no. I can look at 4030. I put something in my note, but to be honest, that was also only a guess, because I was going to look it up and forgot. I put 4730, which is also what I thought now, so maybe it's correct. The next one I do remember, minus 6048. So I wrote out 6 coefficients, and you might think, why is our lecturer so mad and is writing out all these numbers? And why was Ramanujan even madder and went all the way up to q to the 30, which is a lot of work. He made no mistakes. All of his numbers are correct. So a lesser man than he might have computed 30 terms, although I don't think he would have, but he would have certainly not seen the point. But Ramanujan, being Ramanujan, immediately noticed something. He noticed that minus 6048 is the product of minus 24 and 252. So in other words, the coefficient of q to the 6th, the coefficient of q to the 6th, let's put q to the AB, is the product of the coefficients of q squared and q cubed. So it's the product of the coefficient of q to the A and the coefficient of q to the B. It's not always true. For instance, 4 is 2 times 2. This number is not the square of that. This is only if A and B are coprime. So A, B, coprime. For instance, 2 and 3. But he checked this for all numbers up to 30. It was very remarkable. It was proved 1 year later by Mordell in 1917. And this discovery, this multiplicity of the coefficients, I would say as a professional number theorist, is the basis of the most important development in the number theory of the 20th century. So it's really a major, major discovery. It's not just some nice formula. Of course, this particular formula is not the whole point, but the fact that you have this structure, it's now called Hecke theory, led to the Zagier-Langmuntz theory, the theory of automorphic representations. This is the beginning of a huge chapter of, essentially all, in fact, of modern number theory. So that was one thing I want to say. I'll come back to that in a minute. So I'll come back to modular forms, but before I come back to them for the very last part of the lecture, I want to say a word about one thing that was very beautiful, very important, also important to me personally, because I've been very involved with it since the beginning of the theory. And so this was a discovery made by Ramanujan in the last year of his life, so in 1920. He had been quite depressed and written rather sad letters or no letters to Hardy, but in January, only 4 months before his death in April, January 1920, he wrote a very cheerful letter, very happy. I've discovered a most wonderful class of functions, and I call them, he said, the Mach theta functions. So this was in a letter to Hardy. Of course, he never was able to explain anything because he died soon afterwards, and to be honest, he never really explained a lot anyway, but eventually people might have been able to ask him. He did not give any definition, so we don't know what he thought a Mach theta function was, but he gave in this letter 17 examples, but no actual definition. But he did give some properties, and what he said is, now that we understand, 100 years later, they were exactly the right way to look. So basically he said these are functions which are like ordinary theta functions, by which he meant what we call modular forms, but they're not actually modular forms. There's something a bit different. And in particular, they have different asymptotic properties, but he didn't explain, as I said, at all what the properties were. I'm just checking if I left it. So as I gave, so e.g., I'll give the simplest one, I'll just call it M for Mach, he called it F, that everything is F. It's exactly like the first Ramanujan function. So it's again Q hypergeometric. This is exactly the same. Remember Ramanujan, the first one, the G, we took this, and now there are only two differences. All of the minus signs become plus signs, and the denominator, you square everything. So this is exactly of the same sort as G of Q. It's another Q hypergeometric series. But if you write down the other ones, you can, of course, write down thousands, but they won't be interesting. They won't be modular forms, as G was, but they also won't be Mach theta functions, as this is, even though he didn't say. So as I say, this looks very similar, and he explained that it was similar, but not the same, wasn't modular. He didn't say why. This remained a riddle for 82 years until actually my Dutch student in his thesis, Sanders Wekers, PhD in 2002, finally solved the riddle. Now the more general notion is called Mach modular forms, so that is direct, that's the notion of which this is the prototypical case. And so Mach modular forms, I won't give the definition, of course, but they satisfy definition that you can only see if you go from Q to Z. It has to do with the transformation when Z goes to AZ plus B over CZ plus T, but the transformation is much more subtle than in the previous case. So there's an even more hidden symmetry. And now we know this is true, and rather remarkably, these have played a big role in many parts of mathematics since their discovery, in particular in combinatorics, even representation theory of finite simple groups, but also in physics. So for instance, several years ago, I wrote a paper with Atish Dabholkar and Samir Murthy, quite a long paper, so it's now, instead of publishing the paper, it's on the archive bill, it's coming out, we hope soon, when we finish it, as a Cambridge monograph in mathematical physics, and this relates Mach modular forms to the quantum theory, the string theory, to be more precise, string theory of black holes. And this is part of a big development, some of it before our work, some of it after. And for instance, just today, 2 hours after this lecture, Atish Dabholkar, who's in Trieste, will give a lecture which is also being streamed live called 3 Avatars of Mach Modularity. So this is still an active field of research. So that's an absolutely beautiful discovery, a whole new kind of function that in this case, I think we would have not discovered at all without his work, or maybe not yet. So it would have taken more than 100 years later. It's only because he had found these examples that the theory finally could be made precise. So for the very end, I think I've used up an hour since we started, but I was told if I go over 5 minutes, I won't be shot. So I'll trust that that's true. And I'll say very briefly, the last connection, going back to the Rodus Ramanujan identities themselves, with something very nice, which is the icosahedron. And that's why in an earlier announcement of this talk, when there was an older potential title, it was called Ramanujan and Platonic Solids. The icosahedron is, of course, one of the famous 5 Platonic solids that were discovered by Plato's friend, not by him, Theaetetus in 400 BC, roughly. And so there's a connection. So I just want to say very, very briefly a few words about that to end. So the connection between the Ramanujan identities and the dodecahedron. So the dodecahedron, or the icosahedron, more or less equivalent of, let's say, the icosahedron, it's one of the 5 Platonic solids, 2,400 years old. I won't try to draw it because I'm hopeless at drawing, but it has 12 vertices, 20 faces. Icos is the number of faces, so 20 faces, and 30 edges. And it's completely symmetric, and I'm sure you've all seen pictures of it. So many mathematicians of the 19th century studied, but in particular, Klein discovered a wonderful connection, Felix Klein, between the icosahedron, the solution of the general Quintic equation, so 5th degree polynomial equation, which you cannot solve with radicals, but you can solve using something more sophisticated, and the theory of modular forms. And Felix Klein, who was a brilliant expositor, wrote this up as a book called Lectures on the Icosahedron, which is still considered maybe one of the main, certainly one of the greatest mathematical classics of the 19th century, if not of all time. So let me just say very briefly how this goes. So you imagine drawing this thing, which, as I say, I can't draw, but it has here it is. It's got 12 vertices, 30 edges, and 20 faces. You can imagine putting it in a sphere, and then you'll have 30 vertices, which will be points on the sphere. I can take the edge midpoints. They aren't on the sphere, but I can project them from the center onto the sphere, and then similarly the face centers. And so this will give me 3 collections of points on the unit sphere, which is 12 vertices, 30 edge midpoints, and 20 face centers. But the sphere, which is usually called S2, the 2-dimensional sphere, you can think of as the Riemann sphere, which is the complex numbers together with the point at infinity, and so that you can think of as the set of quotients x over y, where x and y are 2 complex variables, and if y is 0, that's the point at infinity, and only the ratio of x over y matters. So that's the sphere, and if you do that, then these 12 vertices are the roots of a polynomial v of xy equals 0. Because any 12 numbers are the 12 roots of a polynomial equation of degree 12. And similarly, the 30 edges are the roots of a polynomial of degree 30. And similarly, the 20 faces are the roots of a polynomial of degree 12. And these were all computed. I should have written this in advance and showed you because it will take a few seconds. So V is fairly simple. It's a trinomial x to the 11th y minus 11 x to the 6th y to the 6 minus xy to the 11. The next one starts x to the 30 minus 522 x to the 26th y to the 5th, x to the 25, excuse me, minus 10,005 x to the 10 y to the 20, x to the 20 y to the 10th. And then it's palindromic, so the next coefficients are the same up to sign, minus 10,005, 522, and 1. And the last one is also palindromic. It's x to the 20 plus 228, x to the 15, y to the 5, plus 494, x to the 10, y to the 10th, and so on. So these are the 3 polynomials that Felix Klein found. And what he showed is that they satisfy a remarkable identity, which is that e squared minus f cubed is 1728 times v to the 5th. So e is a polynomial degree 30, its square is degree 60, f is degree 20, its cube is degree 60, v is degree 12, its 5th power is degree 60. This is a identity between homogeneous polynomials to degree 60. But now surely you will see something very familiar. Here I've a cube and a square, there's some change of sign, e squared minus f cubed. Maybe I got a sign wrong, let's just change it. F cubed minus e squared, but it's actually wrong then, so maybe let's not change it. There's a sign. You see it's exactly like that, e4 cubed minus e6 squared. And so the final relation, this is part of a very long story, which I certainly couldn't tell now anyway. But if you take for x and y, the two Ramanujan functions, I take x to be g of q and y to be h of q, the two of my most beautiful formulas in mathematics, then v is an extremely simple function, namely it's 1. That's the relationship between g and h. So g and h are not independent functions, they're algebraically related by this strange equation. But it's not just that. If you take e of g and h, and f of g and h, so I substitute g of q and h of q for x and y in the other two, then f, well, let's do it, f first and then e, it's more intelligent. F was the one of degree 20. This one is exactly e4. Remember we had e4 and e6, and e4 cubed minus e6 squared is 1728 delta, just as here. So this is indeed e4, but divided by the cube root of delta. And this one is e6 divided by the square root of delta. And so this final formula, I'll stop with that. One sees all of the elements of the theory of modular forms, many formulas due to Ramanujan and the Grobb's Ramanujan identity and the Icosahedron all coming together. If you want to know more about this, I gave a lecture 1 year ago, 3 lectures, and they're on YouTube at the ICTP, so it's easy to find and you can hear more about it. So thank you very much for the invitation and for listening.
Thank you. Thank you very much, Don. Can you hear me?
Yes, but I can't see you. Oh, now I can see you. Oh, that's very nice.
Yeah, oh, that's wonderful. Thank you very much for that excellent lecture and, with very, very beautiful connections. There are some questions here. I will start with one which asked about the two forms being nearly from
Yes.
Ramanujan's laws. So the question from the questioner was this kind of approximation. Is it an approximation, firstly, to say they are nearly, and how useful are such approximations for proceeding further?
Okay, it's not at all about usefulness in this case. First of all, these functions are not useful for anything. He discovered them. They're useful because they're beautiful, which is the definition of useful in mathematics, the only good definition we have. It's not about the approximation. The point isn't just that they're close. The point, I think those formulas have been erased by now. I have the fact that they're nearly equal, but I think I took away the partial explanation. But I gave actually a formula for the beginning of the expansion of both, and this involved not just q, which was very near to 1, I called it e to the minus epsilon, but another number q tilde, which was e to the minus pi squared over 5 epsilon. And that number is extremely close to 1. If epsilon is if q is 0.99, that second number is it's 1 minus 10 to the minus almost 100. So this is a transformation equation. It's a facet of modularity. But the interesting thing, actually I realized last night when I was preparing this lecture, these particular functions that he found are not examples of modular forms or the slight generalization called Jacobi forms. They're examples of a more general kind of function, which is now playing a huge role in quantum topology. And in fact, in this actual room where I'm standing, there are only 4 people because we're not allowed to have congregations. Actually, there are 5 now, but 2 of them are my students who are working on functions Q series, which do not have modular properties, but they have close to modular properties exactly of this type. So this is part of an absolutely beautiful development that's only really beginning to play a role in mathematics in the last 1 or 2 years. In particular, my work with Garuffalidis and several other people. So this is actually typical of a whole very, very interesting class of functions. I have not checked to what extent these particular functions fit, but there's a function that goes beyond modularity and beyond modularity, a new kind of modularity that we've discovered only in the last 2 years, coming somehow from quantum invariance in topology, invariance of three-dimensional manifolds and knots. And in that field, such identities and approximate identities play a role. But I don't know if this is one, and I don't know otherwise how to answer that question.
I have a related question on that. This kind of nearly equal, is that an instance of more general forms of identities? Are there, is there a mathematical way to
Yes, absolutely.
have a theory of nearly equal?
Actually, there is, and I told it, and it's maybe still on the board, except I think that board is too high to see. I should pull it down. So I explained briefly about modularity. And the modular function is one where f of q is essentially equal to f of q tilde. But sometimes, like in the examples of the Ramanujan functions, it wasn't equal. It's maybe a combination of several terms. But the point is that f of q, as well as having an expansion in q, also has an expansion in q tilde. But if q is fairly near to 1, as I said, that means that this alpha is very small. Then this beta is very big because it's a constant over alpha. And so q tilde is incredibly small. And that means that if I look at the right-hand side, which will be some either the same f or some other function, f1 of q tilde, so therefore we have some expansion, b1, b0 plus b1 q tilde. Then if you just look on the computer, since q tilde is typically 10 to the minus 100, what you'll see is it's equal to a constant very nearly. That's what Ramanujan found. But the deep theory is you don't just you aren't just satisfied with it's nearly equal. You say, let's look at the difference, study it, as I did in his case, and found the leading term and then the whole thing. Then find the leading term of that difference, which I wrote down, subtract it. Then it's even more nearly equal to the next thing, find the next, and what you get is a whole expansion. And what you're really seeing is a hidden symmetry that you're discovering numerically with your computer. And the amazing thing to me is that Ramanujan found some of these hidden symmetries without a computer, because the only way I know how to discover them without knowing the theory is to switch on my computer and compute to 1,000 digits, but he could only compute by hand. So how he found it, I don't know. But the true answer is it's not about approximation. It's like all the pure mathematics, it's exact. The right-hand side is not the real series, it's equal to this. Well, both of this has some expansion, this is some other expansion, and these are convergent expansions, but the first term happens to be exactly equal, and the next term has this q tilde. And since q tilde, as I said, when q is 0.99, q tilde is 10 to the minus 100, so you don't see them, so these terms are almost the same. But it's not about approximate quality, it's about a deeper symmetry property that when you invert tau. So it's indeed part of the big story.
The next question is, not this. Another question is very similar in spirit. When you talk about the mock theta functions that Ramanujan was talking about, are they? Does it mean that they are not expressible in terms of the ordinary theta functions, or they are like theta functions? But
that's how he defined it. So to him, theta functions were all functions that you can express in terms of ordinary theta functions. I didn't use that word, but essentially it's the same as modular forms. And all that he said in his letter is these functions, I know, but he didn't say why he knew, but he was right, are not modular functions. They're not theta functions. They're not expressible, but they behave very similarly. And when he explained, so I gave an example, it might still be on the board. I think I called it, n. This was a typical function. If you take this function, and now you take q very near to 1, so this series converges very well if q is small. But if q is very near to 1, let's say it's e to the minus epsilon, it converges very badly, but if you have a big computer, you can still compute it to 100 decibels and find its transformation, its expansion, or q might be some other number, like maybe minus e to the minus epsilon. There are other possibilities. And so what Ramanujan already said in his letter is if you take a function like this m, and you take q to be minus, for instance, e to the minus epsilon, then you get an expansion. I think it began 4 plus epsilon. He didn't give the rest of the expansion, but there is an expansion. This is not what you would get if it were actually a modular form. You would only get 4. There would be no further terms. But the Mach modular form says a correction, but it's something you can understand completely. This is what today we call the shadow of the Mach modular form. It was discovered essentially by Sander Svegers in his thesis. The name I invented, I gave a Bourbaki talk a couple of years later on Svegers' work and explained the theory as it now is, but it was completely Svegers' work. And so the deep part of the Mach theta function is a hidden function that we now call the shadow. And that shadow is an ordinary modular form. So here for this m, I don't remember it, so I won't write it down, but it's something you can write down. So the shadow of a Mach modular form. And to me, a big conundrum of history I would love to solve, but I think we'll never know. Did Ramanujan know the shadow? So in his 17 examples, he gave 17 functions with no explanation. All 17 have shadows. Those shadows are expressible explicitly in terms of theta functions. And I personally believe that he knew that list, but he couldn't formulate what is the relation between them. It's very subtle, and so he didn't tell anyone. But I don't see how he could have found the transformation properties, the asymptotics that he found, if he didn't know. So the deep thing with Mach theta functions or Mach modular forms is that they have what's today, well, it's my word to indicate that it's a little hidden in darkness. Although somebody explained to me the shadow is not hidden in darkness, the shadow is always in the light. But anyway, that's what I meant, is it's hidden. A Mach theta function has a shadow, which is an ordinary modular form. And that's why it behaves differently. If that shadow is different, 0, then it's a usual modular form, and there's no mystery. That was, of course, a very vague answer.
Okay. There is a question from one of the viewers. It asks, this is from Anjan Banik, and he asks, how Ramanujan's mathematics affects even modern science and technology also. Because you mentioned the thing with Atish Davolkar and the work on black holes. So now he's asking...
Okay, technology, I'm the wrong person to ask. You've gotten to know me. I don't even know how to use a mobile phone. I don't understand anything about technology. Mathematics, there are many parts of mathematics, uncountable. Every part of mathematics you find influenced by some of the discoveries Ramanujan made. But the surprise was really the connection with mathematical physics, with modern high-level mathematical physics. I don't mean Newton's laws, but things like string theory, things involving very sophisticated mathematics. And those connections really have only come up, well, with modular forms, they started in the late 90s. I myself, since I'm an expert in modular forms, have often co-authored a paper with physicists because they needed a specialist in modular forms. So I don't know the physics, so I have quite a few papers like that. The one I mentioned was the first one I was involved, I think the first one in physics where Mach modular forms were used explicitly, although a particular Mach modular form that I had found many years earlier was used in work of Witten and I believe Waffe, trying to remember, is it Witten and Moore? There were several papers, Witten and Waffe. So these Mach modular functions came up in quantum field theory and string theory, and they turned out to be absolutely essential. So this joint work with Davolkar and Murty started. I was in Paris at a conference called Modular Forms and Black Holes. And I couldn't resist going because nobody knew there was a connection. And in the conference, there wasn't too much of a connection. There were lectures by mathematicians like me explaining modular forms, and lectures by physicists, and not too much overlap. But one lecture was by another very famous Indian physicist, Ashok Sen, and he told about a riddle, a conundrum that they couldn't solve. In the string theory of black holes, there was a phenomenon called wall crossing. I'm not going to go into it, but it didn't make sense mathematically. And I knew what the answer would be immediately. So after the lecture, I went up to him. This was 2 years maybe after Svegers' thesis, which wasn't known. I said, in my student Svegers' thesis, he discovered a new class of functions. They have this same wall crossing phenomenon. It has to be connected. Can we work on it? And he said, I can't work on it with you because I'm going back. He was leaving the next day from Paris, but he recommended to me to work with Davolkar, who was then in Paris, And he recommended to work with Samir Murti, who's now a professor in London, but was then a postdoc in Paris. And we thought we would spend 1 week just writing a service paper, how you use this theory. It took 6 years for us to work out the theory. It became a whole book. It's a very deep connection. So this field of multiplicative functions turned out not to be peripherally connected, but truly, truly, truly connected with this very high-level string theory of black holes. And there are other examples. The story I mentioned at the very end with the icosahedron, I couldn't go into it, but I started work on it to solve another puzzle in the theory of the quintic, the famous mirror symmetry quintic that was the start of mirror symmetry. This is something the physicists discovered 30 years ago, which has revolutionized algebraic geometry. And there's a deep connection between this original quintic, mirror quintic of the physicists and later mathematicians and the Ramanujan story that I couldn't go into today. So there are many, many cross connections with at least high-level physics. Technology, I don't know if anything that your bank uses Ramanujan's mathematics. I simply don't know.
Okay. One more question, which is before this, I have one more question. These the Rogers-Ramanujan identities, are they instances of a more general theory of identities? Is there a way to generalize these type, or are they too specific to?
Well, yes and no. Of course, there are many, many theories of which they form a special case. But there's not like a specific theory where the identities always have that form. So certainly they're part of the theory of modular forms, as I hope I explained well, that you have this wonderful big class of modular forms, which is my life work, so it's one can study for decades. And they always have surprising identities like E4 cubed minus E6 squared and so on. And the Rogers-Ramanujan identities are exactly examples of how the hidden modularity can lead to these beautiful identities. But a somewhat more concrete thing, again coming from mathematical physics, in quantum field theory, there's a sub-class of quantum field theories that's much better understood mathematically, called conformal field theory, coming from the theory of vertex algebras, vertex operator algebras. And there, these vertex algebras have what are called characters, which are power series in Q, whose coefficient of Q to the K counts how many elements there are in your theory with some quantum state, or some quantum number equal to K, roughly. So they have a physical meaning. And these characters are known, they're almost always hypergeometric series in the sense I explained, but in a large class of functions, it's been proved that they are always modular forms. And the very simplest of the non-trivial vertex operator algebras and conformal field theories is called the 2-5 minimal model. And for that, there are two characters, and they are exactly G of Q and H of Q. So the most direct generalization is that the pair G of Q, H of Q is the pair of characters coming from a vertex operator algebra, this 2-5 minimal model. But if you have some other vertex operator algebras, you will get maybe not 2 functions, but 7 functions, and they might not be independent. They might only span a 4-dimensional space. And that 4-dimensional space will be modular. They will all be modular forms. Functions transform into each other. And the entire theory now of vertex operator algebra, the conformal field theory, it's very important to understand these characters. So that's one big generalization directly of the Rogers-Ramanujan pair. But there are other places. For instance, there are the famous McDonald identities in the theory of Lie algebras, and also in very abstract combinatorics. And the McDonald identities is a huge class of identities, very, very beautiful, of which the connection with the icosahedron is deeply embedded as a primitive example, and the original Rogers-Ramanujan identities are also absolutely there. So there are various beautiful theories that contain them, but there's not a specific way to generalize it to a well-defined notion.
Okay. Yeah. So thanks. There is one last question, which is actually 2 or 3 questions which are the same, asking about books or materials that people can study to understand these things more.
Well,
would you like to give us some?
Of course, that's a very easy question to answer, because when people ask me what they should read or study, I always say whatever I wrote, because it's the only thing I actually know. So I will give 3 sources. One I mentioned, but I think I have to erase, or is there a free space anywhere? So it depends a little, of course, who the person is who is asking. If they're an undergraduate in mathematics, it's one thing. If they're a graduate, it's another. If they're a number theorist, of course, it's again another. But let me give very briefly 3 sources. I have a website. If you go to Google and just type Zagier, my name, homepage, you find it immediately. Everything is there, but the books you cannot download because that's illegal, but you can find them. So one is a book called The 1, 2, 3 of Modular Forms. And this book has 3 authors and 3 chapters, but I'm the author of the first chapter. The first chapter is Modular Forms in 1 variable, the second is 2, and the third in 3. These are different kinds, called Hilbert and Siegel. And today I only talked about this, so this chapter is written by me, and you can find it. It's even on my webpage, but you can't download it. But many people know how to download it illegally. Of course, you can also buy it, and then I get a few pennies royalties. That's written for professional mathematicians, but not for specialists. So you might be even a theoretical physicist or a mathematician in another field. It's a very concise introduction. It's only 100 pages with many, 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 many examples. The point of this text is not a theoretical introduction, but many applications to questions from including even cryptography, transcendence theory, and so on. So this is a serious source if you really want to learn the theory. But otherwise, as I mentioned, I gave 2 lectures at the ICTP, so this again by me, last year, on the Ramanujan identities, the icosahedron. It's more advanced than what I said today, and above all, it's more because it was 3 lectures. But that's on YouTube. You can find it easily, and in fact, I know you've seen it. And finally, I wrote an exposé. I gave a popular lecture on Ramanujan from the first letter to the last letter. The first letter was the letter that Ramanujan wrote to Hardy in 1913 to introduce himself. The last letter was the one he wrote to Hardy again when he was back in India just before his death with the mock theta functions. So this was a big popular lecture I gave, quite successful, in Paris several years ago, exactly the same level as today's lectures. There were some professional mathematicians, some undergraduates, some even advanced high school classes. It went very well, and this one I wrote up. It's on my website, and it should be completely accessible, except for one small proviso. The lecture is given in French and also with the German translation. There is an English translation that actually my wife made, but we never revised it. So you can find it, but only in French and German. But given how many languages you've had your lectures in, just 2 more shouldn't be a problem.
Okay. So thanks very much. Thanks, Don, for that excellent exposition and for answering our questions. Let me thank you and hand over to TV Venkateshwaran for the final summary. Thank you.
Sir, thank you, sir. It was a very interesting talk. I mean, very enlightening talk, and we are also getting quite a lot of comments in our chat section where people have appreciated this talk, and they are saying that they are enjoying this talk. This lecture was organized as part of a program that Vikan Prasad is undertaking called Ramanujan Yatra to celebrate the 100th death anniversary of Ramanujan, and also as a homage and also to popularize mathematics and address math phobia. Thank you for being with us in this program. It's a very wonderful lecture. It's also been telecast through a science channel that Vigan Prasad is operating called indiascience.in. It's a OTT channel. I mean, it's a science channel in India, and it's being live telecast in that science channel right now. So now I would request our director, Dr. Nakul Parasar. Sir, please unmute your mic, and then we can conclude this program. Thanks, sir.
So I would like to thank first all of you for inviting me, for listening, and for making all of this possible. It's a wonderful initiative. Really wonderful.
I finished one more video.
Dr. Parasar, sir, I mean, you have to unmute, and can you speak?
Good, you're very good.
Jemand?
Yeah, I think he is not able to join. There is some communication trouble at his end. So we thank you for being with us for this program, and we thank all the people who have taken part in this program through our social media and also indiascience.in. We thank our director, Dr. Nakul Parasar, and Dr. Ramanujam for ably conducting this program, and also thanks are due to Sri Kumar and Bhaskar, who have been behind the scene arranging this program, and also to people from Max Planck Institute of Mathematics, Bonn, for arranging this at their end, the video and audio arrangement at their end. With this, we will end today's program. If Dr. Nakul Parasar is listening, maybe he can unmute and speak. Otherwise, we will wind. Sri Kumar, just see that, and then we can wind up. No, I think Sri Kumar, I think we can.
Thank you, and bye bye.
Yeah, thank you and bye bye.